A global blackout could begin with a single eruption on the Sun. This is the hidden danger of a coronal mass ejection, a billion-ton storm of solar plasma hurled into space. By the end of this, you will see our star not as a gentle ball of light, but as a capricious force of cosmic chaos. We will uncover how these storms can sneak up on us, why they create phantom currents in the ground, and how they might have even sparked life itself. What does it feel like to know our greatest technological achievements are at the mercy of a star 93 million miles away? The violence of a coronal mass ejection is measured not just in its size, but in its impossible speed. These storms do not drift lazily into space, they are catapulted. The Sun can hurl a billion tons of its own atmosphere outward at speeds ranging from 250 kilometers per second to well over 3,000 kilometers per second. To put that into a scale our minds can grasp, at its absolute fastest, a coronal mass ejection could cover the distance from the Earth to the Moon in roughly 15 minutes. A journey that took the Apollo astronauts 3 days would be, for this wall of solar plasma, a brief sprint. Scientists track this terrifying velocity using a fleet of solar sentinels, spacecraft like SOHO and STEREO. These observatories act as cosmic traffic cameras, positioned at strategic points to watch the leading edge of a coronal mass ejection as it billows out from the Sun. By taking sequential images, they can measure how far the storm front moves in a given time, calculating its speed with chilling precision. This is not the steady, persistent flow of the normal solar wind, which streams past Earth at a comparably gentle 400 kilometers per second. A coronal mass ejection is a shock wave, a supersonic explosion of magnetized gas. And it is this raw, explosive speed that strips away our sense of security. A storm leaving the Sun can be aimed directly at us, and we might have less than a single day's warning before it slams into our planet's magnetic field. The vastness of space offers no real cushion, no time for a leisurely preparation when the attack is moving at millions of miles per hour. This first fact sets the stage for everything that follows, a fundamental truth about these events. They are not just powerful, they are devastatingly fast. But what happens when that speeding wall of chaos does not hit us directly? The danger takes a far stranger, more insidious turn. This distinction is absolutely critical, yet it is one of the most common points of confusion. When news reports warn of a solar storm, they are often talking about two very different things happening at once. The first is a solar flare. Think of a flare as a flashbulb, an instantaneous and blindingly bright eruption of energy across the entire electromagnetic spectrum. It is a burst of light, primarily X-rays and ultraviolet radiation, that travels at the speed of light itself. From the moment we see the flash, we have just over 8 minutes before that radiation washes over our planet, potentially disrupting radio communications and overloading satellite electronics. It is a sudden, powerful, and very fast signal, but it is not the main event. That title belongs to the coronal mass ejection. While the flare is the flash, the coronal mass ejection is the cannonball. It is not light but physical matter, a colossal cloud of the Sun's own atmosphere, a billion tons of magnetized plasma torn from the corona and hurled into the void. This is the storm cloud that moves at a fraction of light speed, taking hours or days to arrive. They are siblings born from the same chaotic magnetic activity on the Sun, and they often erupt together. A powerful flare can be the herald, the brilliant signal that a coronal mass ejection has just been launched. But here is the strange part: one can occur without the other. You can have a spectacular X-class solar flare with no coronal mass ejection following it. Conversely, a massive, planet-threatening coronal mass ejection can erupt from the Sun with only a faint, almost unnoticeable flare. This is why understanding the difference is so vital for space weather forecasters. The flash tells you something exploded, but the cloud tells you what, and more importantly, when it is coming. Confusing the two would be like hearing thunder and assuming the lightning strike is still minutes away, when in reality, the sound and the bolt are part of the same moment, followed by a completely different danger, the flood. So we must separate the signal from the storm, and if the storm, the coronal mass ejection, is the real threat, then a terrifying question emerges: how do we know if one is actually coming for us? That billion-ton cloud speeding toward us is more than just a wave of hot particles. It is a prison for a magnetic monster. The true destructive power of a coronal mass ejection is not carried in its plasma, but in the invisible, twisted magnetic field frozen inside it. As the sun's atmosphere is ripped away, the complex magnetic loops that once tethered it to the solar surface are carried off into space, trapped within the super-hot gas. Picture this not as a smooth balloon of energy, but as a knotted, writhing snarl of magnetic force lines, a chaotic structure billions of miles across. This embedded magnetic architecture is what turns a solar cloud into a planet-shaking event. When this traveling knot of magnetism finally reaches Earth, it does not simply bounce off our planet's own magnetic shield, the magnetosphere. Instead, the two fields engage in a violent, invisible dance. If the orientation is wrong, specifically if the incoming field is pointed southward, opposite to Earth's northward pointing field at the dayside, something extraordinary and dangerous happens: magnetic reconnection. It is a fundamental process in plasma physics where magnetic field lines break and reconnect in a new configuration, releasing staggering amounts of stored energy. In this case, the CMEs southward field can forcibly connect with Earth's northward field, effectively ripping open a temporary breach in our planetary defenses. It is like two powerful magnets snapping together with catastrophic force, but on a global scale. This reconnection funnels the raw energy of the solar storm directly into Earth's upper atmosphere, overloading electrical circuits in the sky we never knew existed. It is this precise magnetic alignment, this southward punch, that determines everything. A coronal mass ejection with a northward field might simply glance off, causing beautiful auroras and little else. But the same-sized storm with a southward field becomes a Carrington-level threat, capable of inducing ground currents strong enough to melt the copper in power grid transformers. We are left with a chilling realization: our fate hinges not on the size of the storm, but on the invisible orientation of a magnetic field we cannot control, a cosmic coin toss played with the fury of a star. And once that energy is inside our shield, it seeks the most unexpected paths to the ground. The most violent solar storm in recorded history began with a simple white light flare. On September 1, 1859, amateur astronomer Richard Carrington was sketching a group of enormous sunspots when he witnessed two blinding beads of light erupt from the solar surface. He had just documented the flash that heralded a coronal mass ejection of unimaginable power, a direct hit on our planet. The effects were both beautiful and terrifying. Within hours, Earth's skies erupted in a firestorm of color. Auroras, normally confined to polar regions, blazed so brightly that people across North America and Europe could read newspapers by their crimson and green glow at midnight. They were seen as far south as Cuba and Hawaii, with gold miners in the Rocky Mountains waking up and starting breakfast because they thought the dawn had arrived. But the true measure of the storm's power was found not in the sky, but in the telegraph offices, the high technology of the age. Operators received severe electric shocks from their equipment. Telegraph papers caught fire from sparks. Most astonishingly, some found they could disconnect their batteries entirely and still send messages for hours, powered solely by the auroral currents flowing through the wires. The Earth itself had become a temporary battery. We remember this as the Carrington event, a benchmark for the worst-case scenario. Yet the geological record whispers a far more unsettling truth: Carrington was not the worst our sun can do. In the year 774, Earth was bombarded by a proton storm so intense it left a permanent scar in the planet's memory. Scientists analyzing ancient tree rings discovered a staggering spike in radioactive carbon-14, a clear fingerprint of a cosmic ray influx a staggering 10 times stronger than the Carrington event. This MEAC event, named after the researcher who found its signature, left no eyewitness accounts of glowing skies, likely because human civilization at the time lacked the global technology to notice or record its electromagnetic effects. But if such a storm struck today, its impact would be beyond catastrophic. This evidence forces a profound shift in perspective. We are not waiting for a one-in-a-thousand-year event that already happened in 1859. We are living on a planet that is periodically, inevitably struck by solar superstorms. The Carrington event is not a ceiling, it is merely a data point, a recent warning from history of what our star is fully capable of delivering again. And if our modern world is so much more vulnerable, what would happen if a storm arrived not from the sun, but from somewhere else entirely? The sun's most dangerous storms are not always the loudest. There exists a class of coronal mass ejections so quiet, so subtle, they can slip past our most vigilant solar observatories until they are almost upon us. Forecasters call them stealth coronal mass ejections, or more ominously, problem storms. Unlike their dramatic cousins that erupt with a brilliant solar flare, these events seem to simply detach from the sun's atmosphere and drift away like a ghost ship leaving port in a dense fog. They lack the classic signatures, the bright flash of a flare or the distinctive bright front in the coronagraph images that scientists use as an early warning siren. The problem is one of contrast. A stealth coronal mass ejection is often born from a region of the sun with a weak and incredibly tangled magnetic field. Instead of a single, powerful explosion that blasts material clear of the solar surface, the magnetic field in these areas slowly reconnects and unravels at a low altitude, allowing a huge cloud of plasma to just float away. It does not have the same punch of energy to make it stand out brightly against the blazing backdrop of the sun's outer corona. To our instruments, it looks like a faint, diffuse shimmer, easily mistaken for background noise or the steady stream of the solar wind. This makes them a forecaster's nightmare. While we might have days of warning for a classic, fast-moving coronal mass ejection, a stealth storm could be announced with only a handful of hours before impact, or in the worst cases, we might only realize it was coming after the first particles begin to dance in our magnetosphere. It is a chilling reminder that our technological watchtowers have blind spots, and that the sun's chaos can manifest not just in violence but in perfect, undetectable silence. This hidden threat forces us to ask, if a storm can arrive with so little warning, how exactly are we supposed to see it coming at all? Even after the initial shock of a coronal mass ejection passes, the danger for our technology in space is just beginning. The storm's arrival triggers a secondary, insidious effect deep within Earth's own protective magnetic architecture. When the leading edge of that billion-ton plasma cloud slams into our magnetosphere, it acts like a cosmic hammer blow, violently compressing the entire magnetic field on the daytime side of our planet. This sudden squeeze does not just create auroras, it sends a powerful shock wave rippling through the Van Allen radiation belts, those donut-shaped zones of trapped charged particles that encircle Earth. Within those belts, the compression acts like a giant particle accelerator. Electrons already trapped there get a tremendous, violent push. They are whipped to velocities approaching the speed of light, gaining energies millions of times greater than a medical X-ray machine. Space physicists have a grimly accurate name for these ultra-relativistic particles, killer electrons. The name is no exaggeration. These electrons are so energetic and penetrating that they can sail right through the aluminum skin of a satellite. They do not just cause temporary glitches, they can physically burn out microscopic circuits, create false commands in a spacecraft's computer brain, and degrade solar panels, permanently crippling multi-million-dollar infrastructure. This process, known as radial diffusion, turns the radiation belts into a minefield. Waves of energy from the compressed magnetosphere scatter the particles inward, pushing them into more intense regions of the magnetic field where they gain even more speed through wave-particle interactions. It is a vicious feedback loop of acceleration. The terrifying result is that the most hazardous period for satellites in medium Earth orbit, the home of critical global positioning and communications constellations, often occurs not during the storm's main arrival, but in the days and even weeks that follow. While we on the ground watch the beautiful auroral curtains fade, a silent, invisible bombardment is underway high above, a lingering radiation hangover that can doom spacecraft one delicate circuit at a time. This reveals a profound vulnerability. Our orbital civilization does not just face a temporary blackout, but a sustained, attritional assault from a star we thought was safely distant. And if the Sun can create such destructive particles around our own world, what other, more beautiful havoc can it wreak across the solar system? Our own Sun is a formidable force, but in the grand stellar neighborhood, it is surprisingly well behaved. To find the true titans of solar violence, we must look to the stars, and what we see there redefines the very scale of a coronal mass ejection. Using space telescopes like Kepler and TESS, astronomers have not just theorized about these events, they have captured them in the act, witnessing super-sized CMEs erupting from distant suns. The most violent offenders are often red dwarf stars, small, cool, and incredibly temperamental. These stars can possess magnetic fields hundreds of times more tangled and intense than our suns. The eruptions they produce are not merely larger, they are in a different league of cosmic fury entirely. Scientists detect them through a specific, terrifying signature. First, a monstrous stellar flare causes a sudden, sharp spike in the star's brightness, particularly in high-energy ultraviolet and X-ray light. Then, in the aftermath, comes the real clue, a distinct dimming. This is the telltale shadow of the coronal mass ejection itself, as the billion-ton cloud of ejected stellar material billows out and temporarily blocks a fraction of the star's own light from our view. These are not solar storms, they are stellar hurricanes. The energy released in these events is thought to be thousands, even millions of times more powerful than the Carrington event. For any rocky planet orbiting in the so-called habitable zone of such an active star, the consequences would be apocalyptic. A single one of these super CMEs slamming into a planet with a weak magnetic field could do more than just induce auroras. It could literally blow the planet's atmosphere away into space, stripping it bare over geologic time. This discovery forces a profound and humbling perspective shift. The coronal mass ejections we fear from our own sun are, by cosmic standards, relatively gentle. We are living next to a stable, middle-aged star, a cosmic pacifist compared to the volatile youth that dominate the galaxy. Our planetary magnetic field is not just a shield for our technology, it is a shield for our very sky, a fragile bubble preserving the air we breathe against a universe filled with far more violent stellar winds. It makes our own solar threat seem almost quaint, but it also raises a new and unsettling question about our own past. Could such an event have happened here long before human history began? The true power of a coronal mass ejection does not end in the upper atmosphere. It flows directly into the Earth itself, seeking out the very skeleton of our modern world. When the planet's magnetic field is violently shaken by a solar storm, it does more than just paint the sky with light. This rapid, chaotic fluctuation of the magnetic field acts like a massive, invisible generator, one that uses the entire planet as its coil. The result is a phenomenon known as a geomagnetically induced current. These are not the familiar, fast-moving alternating currents in your home's wiring. These are slow, powerful, direct currents that flow through the ground itself and through any long conductor buried or stretched across it. the Earth becomes a temporary battery and our infrastructure becomes its unintended circuit. Power grids are especially vulnerable. The high-voltage transformers that form the backbone of our electrical system are designed to handle specific frequencies of alternating current. When a geomagnetically induced current, a kind of electrical tide, pushes a steady flow of direct current into this delicate network, it forces the transformers to operate outside their safe limits. The core of the transformer can become saturated, meaning it can no longer properly regulate the voltage. This causes the transformer to overheat, not over minutes, but potentially over hours, leading to internal damage or even a catastrophic fiery failure. The most dramatic example of this occurred in the early hours of March 13, 1989. A powerful coronal mass ejection struck Earth's magnetosphere, triggering intense auroras seen as far south as Florida and Cuba. But in Quebec, Canada, the real drama was underground. Geomagnetically induced currents flooded into the Hydro-Quebec power grid. At 2:44 in the morning, protective relays sensed the instability and began to trip offline in a cascading sequence. Within 90 seconds, the entire province of Quebec, home to 6 million people, was plunged into a blackout. The outage lasted for over 9 hours, halting subways, closing schools and businesses, and leaving people shivering in the late winter cold. All of this chaos was caused not by a downed power line or a failed generator, but by a silent, invisible current induced by a storm that began on the Sun 93 million miles away. It was a stark, undeniable lesson in our planetary vulnerability. Our greatest technological networks are not just connected to power plants, they are, in a very real sense, wired directly to the Sun. And that connection can become a fatal flaw when the star decides to send a surge. Sometimes the Sun does not just send a storm, it sends a hunter. In the chaotic ballet of solar eruptions, one of the most feared scenarios is not a single coronal mass ejection, but a chase. The process begins with an initial, powerful eruption that tears itself free from the Sun and begins its journey across the void. This first cloud might be moving at a formidable 1,000 kilometers per second. But then, hours or even days later, from the same volatile region of the Sun, a second coronal mass ejection erupts. This one is faster, more energetic, accelerating to perhaps 1,500 kilometers per second. In the vast emptiness between planets, the second, speedier storm begins to overtake the first. It does not simply merge with it gently, it violently plows into the slower-moving material from the initial eruption. The faster cloud scoops up the preceding plasma, compressing and entangling the magnetic fields of both events into a single, monstrous shock front. Space weather scientists have a vivid and perfectly apt name for this: a cannibal coronal mass ejection. The resulting hybrid storm is far more dangerous than the sum of its parts. The compression amplifies the magnetic field strength, creating a more intense and tangled magnetic architecture. It also packs a denser concentration of energetic particles. Think of it not as two waves combining, but as a tsunami overtaking and absorbing a smaller wave, growing taller and more powerful in the process. When this combined front finally reaches Earth, the impact is profound. The sudden, compounded pressure on our magnetosphere is immense, and the complex, reinforced magnetic field inside the cloud has a much higher chance of aligning in that dangerous southward orientation, ripping open our defenses wider and for longer. This makes cannibal coronal mass ejections a top-tier concern for forecasters. Predicting the severity of a simple storm is difficult enough, but predicting the chaotic interaction of two or more storms in transit is a monumental challenge. A seemingly moderate event on the solar forecast can transform into an extreme geomagnetic storm by the time it reaches our doorstep, all because one eruption consumed another on the highway of interplanetary space. It reveals a layer of solar violence we are only beginning to map, where the Sun's fury can compound itself en route, building a perfect storm from separate pieces of its own anger. A planet's magnetic field is not a perfect static bubble. It is a living, breathing entity constantly sculpted by the solar wind. This relentless stream of particles from the sun acts like a cosmic breeze, pressing against the magnetic shield on the day side and stretching it into a long, comet-like tail on the night side. But when a coronal mass ejection arrives, that gentle breeze becomes a hurricane, and the reshaping is violent and profound. Jupiter offers the most spectacular example in our solar system. Its magnetosphere is the largest physical structure attached to a planet, so immense that if it were visible in our night sky, it would appear larger than the full moon. Yet even this titanic magnetic field is not immune to the sun's fury. Under normal conditions, the solar wind compresses Jupiter's dayside magnetosphere, holding its immense power in check. But on the night side, the field is stretched into a magnetotail that may extend hundreds of millions of miles, all the way to the orbit of Saturn. When a coronal mass ejection slams into this system, the effect is like a hammer striking an anvil. The dayside compression becomes extreme, pushing the boundary inward by millions of miles in a matter of hours. The shock wave races through the magnetosphere, energizing particles to incredible levels and triggering auroral storms on Jupiter's poles that would dwarf our entire planet. These are not the gentle curtains of light we see on Earth, but continent-sized infernos of radiation, visible across the electromagnetic spectrum. This dynamic interaction proves a fundamental truth. Coronal mass ejections are not just passing weather, they are a primary architect of planetary space environments. They dictate the shape, size, and very behavior of a planet's magnetic shield. For worlds like Earth, this constant sculpting is a protective dance. For worlds without a strong magnetic field, like Mars or Venus, the effect is far more erosive, as the storm can directly strip away the atmosphere over time. Our planet's protective cocoon is not a fixed fortress, but a shape-shifting barrier, forever being molded by the invisible hand of the sun. And sometimes that hand does not just shape the field, it uses it to create a sound we can almost hear. The upper atmosphere can brew a storm unlike any on Earth. In 2014, satellite data revealed something utterly unexpected. A churning vortex of plasma nearly 1,000 kilometers wide, spinning silently above the North Pole. It was not a cloud formation, but a space hurricane, a permanent feature of our planet's polar sky during a specific, quiet phase of the solar wind. This colossal structure, with a calm central eye and vast, sweeping spiral arms, rained not water, but energetic electrons directly into the ionosphere below. The energy transfer was immense, a continuous, swirling downpour of charged particles from the magnetosphere above. While not the direct result of a single, violent coronal mass ejection, this phenomenon is a close relative, a different manifestation of the same fundamental solar-planetary interaction. It occurs when the interplanetary magnetic field, the sun's magnetic influence carried on the solar wind, points steadily northward. This orientation allows the solar wind's energy to funnel into the polar regions in a stable, rotating pattern, rather than in the explosive bursts of a geomagnetic storm. The space hurricane demonstrates that the sun's influence is not merely episodic violence, but also includes these sustained, almost serene states of intense atmospheric chemistry. It is a beautiful and bizarre form of space weather, proving that even when the sun is not lashing out with a coronal mass ejection, it is still painting complex, invisible patterns in the sky, patterns that fundamentally alter the electrical properties of the air high above our heads. This reveals a layer of constant, dynamic interaction we are only beginning to map, where the boundary between space and our world is not a wall, but a seething, energetic frontier. The moon carries a permanent record of the sun's fury. Without an atmosphere or a magnetic field to deflect them, every charged particle the sun has ever hurled into space has had a clear shot at the lunar surface for over 4 billion years. When a coronal mass ejection strikes the moon, its high-energy ions like helium and neon do not just bounce off, they slam directly into the dust and rock, becoming physically embedded in the top layers of the regolith. This process is a form of cosmic tattooing, where each violent solar storm leaves a permanent microscopic signature in the lunar soil. These implanted particles are, in effect, fossilized coronal mass ejections. For scientists, the Moon has become an invaluable history book, its pages written not in ink but in trapped solar wind. By carefully analyzing samples returned by the Apollo astronauts, or by using instruments on orbiters to study the soil's composition from afar, researchers can perform a kind of solar archaeology. They can drill down metaphorically through the layers of dust which accumulate slowly over eons. By dating a specific layer and then measuring the concentration and type of solar particles trapped within it, they can reconstruct the Sun's behavior at that precise moment in deep time. This has revealed astonishing chapters in solar history, including evidence of periods when our young Sun was a far more violent and tempestuous star, erupting with superstorms at a frequency we would find terrifying today. This lunar archive offers something Earth never can, a continuous, unedited record. On our planet, erosion, plate tectonics, and our protective magnetic field constantly scrub away these ancient fingerprints. The Moon, geologically dead and exposed, preserves them perfectly. So while we look to the future with concern over the next big solar storm, we are also learning to read the past in the silent, gray dust of our nearest celestial neighbor, finding that the Sun's history is literally written in the stars, or at least in the soil they bombard. Our technological web is not the only thing vulnerable to these invisible storms. The human body itself faces a direct and lethal threat from the charged particles a coronal mass ejection hurls across space. For an astronaut outside the protective cocoon of Earth's magnetic field, a major solar eruption is not an abstract risk, it is a potential death sentence. The primary danger comes from protons, the positively charged nuclei of hydrogen atoms, which the shock wave of a CME can accelerate to nearly the speed of light. This creates a sudden, intense squall of radiation, a particle rain far more concentrated and immediate than the constant, diffuse background drizzle of galactic cosmic rays from deep space. The difference is one of dosage and timing. Think of cosmic rays as a steady, low-level exposure, like living at a high altitude. A coronal mass ejection is like walking directly into the beam of an unshielded X-ray machine, a sudden, overwhelming blast. Inside the relatively safe orbit of the International Space Station, astronauts are still partly shielded by Earth's magnetosphere, but during a powerful event, they are instructed to move to the most shielded modules of the station, as radiation levels can spike dangerously. The real peril, however, lies beyond that protective magnetic bubble. On the surface of the Moon or in a spacecraft en route to Mars, there is no planetary shield to deflect the onslaught. An astronaut caught in a direct hit from a Carrington-level storm without adequate warning or shelter could receive a radiation dose measured in hundreds of millisieverts within hours. To put that in perspective, that is more radiation than a nuclear power plant worker is allowed to absorb in an entire year, all delivered in a single, terrifying event. The immediate effects could include acute radiation sickness, nausea, vomiting, and a catastrophic drop in blood cell counts. But the longer-term, more insidious threat is a drastically elevated lifetime risk of developing cancer as the high-energy particles shred cellular DNA. This is not a secondary engineering problem, it is a primary biological barrier. Planning for a multi-year mission to Mars becomes a terrifying game of probability, calculating the odds that a crew will be exposed to a lethal solar storm while millions of miles from any hope of a rapid return or advanced medical care. Storm shelters on a spacecraft or a lunar base lined with water or polyethylene are a necessity, not a luxury. But they add immense weight and complexity, and they require one crucial element we do not always have: time. A warning: the specter of a stealth coronal mass ejection, arriving with little notice, represents a nightmare scenario for mission controllers. It means the difference between a crew safely hunkering down in their shielded haven and being caught utterly exposed on a spacewalk or a planetary surface with the sky suddenly turning lethal. This fact transforms deep space from a frontier of exploration into a gauntlet of invisible arrows, where our greatest adventure is shadowed by one of our oldest stellar fears. The first tangible warning of a solar storm arrives not with a bang, but with a sudden, profound silence. For a radio operator on the sunlit side of Earth, it can happen in an instant. One moment, a clear shortwave broadcast is bouncing perfectly off the upper atmosphere, carrying voices or data across continents. The next, the signal dissolves into static, as if someone has simply pulled a cosmic plug. This abrupt radio blackout is not caused by the coronal mass ejection itself, which is still days away, but by its brilliant flash of a sibling, the solar flare. Traveling at the speed of light, the intense burst of X-rays and extreme ultraviolet radiation from the flare reaches our planet in just over 8 minutes. When this wave of high-energy light slams into the daytime ionosphere, the uppermost electrically charged layer of our atmosphere, it acts like a cosmic flashbulb. The radiation violently strips electrons from atoms and molecules in a process called ionization, causing the density of free electrons in the ionosphere to spike dramatically in an event known as a sudden ionospheric disturbance. Think of the ionosphere as a mirror in the sky, one that radio signals use to bounce over the horizon for long-distance communication. A sudden ionospheric disturbance does not crack this mirror, it turns it into a sponge. The suddenly super-dense ionized layer absorbs the radio energy instead of reflecting it, causing signals to fade or vanish completely. These blackouts are immediate, localized to the hemisphere facing the sun, and can last from several minutes to a couple of hours until the ionosphere recovers its equilibrium. For pilots, maritime crews, and amateur radio enthusiasts, it is a frustrating but critical heads-up. That wall of static is the first direct evidence on Earth that a major solar event has just occurred, a silent siren announcing that a far slower, more physical threat has been launched and is now on its way. It is a stark reminder that even at the speed of light, a warning can feel agonizingly short, a brief whisper of static before the real storm arrives. The scale of these events defies our everyday understanding of distance. We often visualize a coronal mass ejection as a focused beam, a solar shotgun blast aimed at a single point in space. But the reality for the largest eruptions is far more encompassing and far more terrifying. The most massive coronal mass ejections do not travel as a narrow stream, they expand. As that billion-ton cloud of magnetized plasma pushes away from the sun, it billows outward in all directions, forming a colossal, hollow bubble of stellar material. By the time such a structure travels the 93 million miles to Earth's orbit, it can be wider than the sun itself. Our entire planet, from pole to pole, would not just be struck by the leading edge of this storm, it would be swallowed whole, immersed for hours or even days in the churning, electrified fog of the sun's own atmosphere. We have a chillingly close example of exactly this scenario. In late July of 2012, the sun unleashed one of the most powerful coronal mass ejections in the space age. It erupted from a massive sunspot group, but its trajectory was just off the Sun-Earth line. It missed us by about a week's worth of orbital travel, but humanity's instruments did not miss it. The STEREO, a spacecraft positioned as a solar sentinel ahead of Earth in its orbit, was perfectly placed to take the direct hit and measure the storm's true dimensions. The data was staggering. The plasma cloud that washed over the spacecraft was so vast that if its path had intersected with Earth, our planet would have been completely enveloped. There would have been no glancing blow, no brief period of impact. Instead, Earth's entire magnetosphere, that protective magnetic bubble that normally deflects the solar wind, would have been submerged inside the coronal mass ejection itself. Think of the difference between being hit by a wave at the beach and being trapped underwater in the turbulent wake of a sinking ship. This total immersion maximizes every possible danger. Our magnetic shield would be bathed on all sides by the CMEs' chaotic, twisted magnetic field, dramatically increasing the odds of a prolonged, southward-aligned punch that could rip it open for an extended siege. The relentless pressure of the dense plasma would keep the magnetosphere compressed, unable to rebound. For satellites, this means no temporary respite on the leeward side. They are inside the storm, subjected to a continuous bombardment of high-energy particles and intense electrical charging for the entire duration. On the ground, the geomagnetically induced currents flowing through power grids would not be a brief spike, but a sustained, potentially overwhelming tidal surge, pushing transformers and infrastructure toward failure over many hours. The July 2012 event was a direct hit on our technology, but a near miss for our civilization. It passed through the orbit we occupied just 1 week earlier. It serves as a sobering proof of concept, a cosmic demonstration that the Sun is fully capable of casting a net so wide we cannot slip past it. Our safety, it seems, relies not just on the storm's power, but on the sheer, merciful luck of geometry. The same solar violence that threatens our existence today may have been the very spark that ignited it. This leads us to a profound and beautiful paradox. While coronal mass ejections represent an existential risk to our advanced civilization, they might have been the essential midwife to life itself in our planet's infancy. Billions of years ago, our Sun was a far more tempestuous star, erupting with powerful flares and coronal mass ejections at a frequency that would be unthinkable today. The young Earth, meanwhile, possessed a very different atmosphere, a thick, hazy mix of gases like methane, ammonia, water vapor, and carbon dioxide, with little to no free oxygen. The classic puzzle of abiogenesis, how life arose from non-living matter, has long centered on where the energy came from to forge simple gases into the complex organic molecules like amino acids and nucleic acids, the literal building blocks of biology. Lightning strikes and volcanic heat were considered, but some astrobiologists now point a finger squarely at the sky, at the young Sun's relentless storm activity. The hypothesis is electrifying, literally. When a powerful coronal mass ejection from that ancient Sun slammed into Earth's primordial atmosphere, it would have done more than just create auroras. The intense shock waves, the bursts of ultraviolet and X-ray radiation, and the torrents of energetic particles would have violently agitated the atmospheric soup. This colossal input of energy could have broken the strong chemical bonds in those simple gases, forcing the fragments to recombine into more complex carbon-rich compounds. It is a process akin to the famous Miller-Urey experiment from the 1950s, where scientists simulated early Earth conditions with electrical sparks in a flask of simple gases and produced organic molecules. But instead of a lab electrode, the spark for the entire planet may have been a solar superstorm. The frequent planet-enveloping coronal mass ejections of the Hadean and Archean eons could have served as a global, continuous chemical reactor, showering the oceans and land with a rain of prebiotic material. This idea reframes the Sun's fury not as mere destruction, but as a form of cosmic alchemy. The same processes that today could induce fatal currents in our power grids might, in the deep past, have induced the first currents of metabolism in a primordial soup. It suggests that the ingredients for life are not a rare cosmic accident, but a probable and even expected byproduct of a solar system's violent youth, where a stormy star relentlessly hammers its orbiting worlds with the energy of creation. This transforms our relationship with these events from one of pure dread to one of awe, recognizing that the same force that could end our technological age may have been the essential catalyst that allowed any age to begin at all. And if solar storms helped write life's first chapter on Earth, what other, stranger signatures might they leave across the cosmos? The sky itself can break its own rules during a solar siege. Auroras are not meant for the tropics. They're dancing green curtains confined by physics to a ring around Earth's magnetic poles. But a coronal mass ejection of sufficient fury possesses a terrible power. It can shove that entire auroral oval, that crown of light, thousands of miles toward the equator. During an extreme geomagnetic storm, the violent compression and energization of our magnetosphere expands the zone where solar particles can rain down into the atmosphere. The result is a forbidden spectacle, the polar lights appearing where they simply should not be. In March of 1989, they blazed over Florida and Texas. During the Carrington event, they turned the skies over Cuba and Hawaii into canvases of crimson and emerald. For people living in these latitudes, it is a moment of sublime disorientation, witnessing a cosmic light show that belongs to another part of the world entirely, a beautiful symptom of a planet-wide magnetic fever. Yet there exists an even stranger, more pervasive glow born from these storms. Alongside the electrons that create the classic shimmering curtains, a coronal mass ejection also hurls a torrent of high-energy protons. These heavier, more penetrating particles behave differently. They are not as easily funneled by magnetic field lines toward the poles. Instead, they can slam into the upper atmosphere almost anywhere on the planet, creating what scientists call a proton aurora. This is not a structured curtain of light, but a diffuse, faint veil. It often manifests as a uniform, pinkish or reddish haze that can linger for days, visible even in broad daylight as a peculiar wash of color in the sky. Historical reports from the Carrington event describe this exact phenomenon, with widespread, unsettling blood-red skies so intense that many believed distant cities were engulfed in massive fires. This global glow is the signature of the storm's most energetic infantry penetrating deeper into our defensive lines, a subtle but omnipresent reminder that during a solar attack, no sky on Earth is truly safe or normal. The auroras we admire are merely the visible embroidery on a far larger and more invasive tapestry of light. The sky's silent light show hides a deeper, invisible symphony. While no sound can travel through the vacuum of space, we have found a way to listen to a coronal mass ejection, to hear the storm's hidden voice. This is made possible through a process called data sonification, where scientists translate the raw numbers from our space weather sentinels into sound. As a coronal mass ejection washes over a spacecraft like the Wind satellite, its instruments record every shudder, a constant stream of data on magnetic field strength, direction, and the density of charged particles. These numbers are more than just graphs on a screen. They are a recording of the storm's physical structure in time. Researchers can assign specific audio frequencies to different values, turning a spike in magnetic turbulence into a rising whistle, or a wave of dense plasma into a deep, rumbling tone. The result is an eerie, otherworldly soundscape. What you hear is not an artist's interpretation, but a direct auditory translation of the violence. You might hear the sharp crackle of a shock wave as the leading edge of the storm slams into the solar wind, followed by a chorus of whistles and chirps as tangled magnetic fields writhe and reconnect. The chaotic static represents a hail of high-energy particles pummeling the spacecraft's sensors. It is the sound of raw cosmic weather, a ghostly radio transmission from the heart of a billion-ton plasma cloud. But this is far more than a scientific curiosity. Our ears are remarkably good at detecting patterns and rhythms that our eyes can gloss over in a visual graph. By listening to the data, researchers can sometimes identify subtle structures within the storm, recurring frequencies that hint at hidden waves or resonant cavities within the magnetic chaos. It turns a silent, invisible event into something visceral, something we can experience with a different sense entirely. In a very real way, we are giving the storm a voice, and what it says is a complex language of whistles, roars, and static that we are only just beginning to understand. A solar storm's confusion does not stop at the edge of our power grids. It spills over into the living world, scrambling the ancient maps written in magnetism that countless creatures rely on to survive. For migratory animals, Earth's magnetic field is not an abstract force. It is a highway in the dark, a compass etched into their very biology. Birds, sea turtles, monarch butterflies, and even some bacteria possess a mysterious sensory ability called magnetoception, allowing them to detect the planet's magnetic pull and use it to navigate across continents and oceans with pinpoint accuracy. But during a geomagnetic storm, that reliable map dissolves into chaos. The rapid, violent fluctuations in the magnetic field caused by a coronal mass ejection create a form of global interference, a deafening static over the natural signal these animals have evolved to follow. The consequences are both subtle and devastating. Scientific studies have documented a clear, troubling correlation. During periods of intense solar activity, the delicate internal compasses of these travelers seem to fail. Homing pigeons, renowned for their unerring ability to find their lofts from hundreds of miles away, show significantly poorer race results and higher losses when solar storms rage. They become disoriented, circling aimlessly or flying in completely wrong directions, as if their guiding star has suddenly begun to spin. The effect reaches into the deep ocean. Researchers have analyzed decades of data on whale strandings, particularly for species like sperm whales that undertake long migrations. The findings point to a startling pattern. A statistically significant increase in mass beachings occurs in the days following a major geomagnetic storm. The theory is haunting. These deep-diving navigators, who use subtle magnetic variations to chart their course along underwater mountain ranges, become lost in the distorted field. They might mistake a gently sloping beach for a deep sea trench, swimming toward land with fatal confidence. For birds undertaking transcontinental journeys, a disrupted magnetic sense can mean missing crucial feeding grounds or arriving at nesting sites too exhausted to breed. This is not a minor inconvenience, it is a matter of life and death on a species-wide scale. This bizarre fact forces a profound expansion of our perspective. A coronal mass ejection is not merely a technological or atmospheric event, it is a biological phenomenon. The same invisible forces that induce currents in copper wires can induce disorientation in a creature's brain. It reveals a hidden vulnerability in the fabric of nature itself, showing that the sun's fury can rewrite the oldest navigational codes on Earth, leaving even the most seasoned natural travelers lost in a world they thought they knew. This perfect storm of solar violence and biological confusion leads us to a final, crucial perspective, one that reframes our entire relationship with these events. We are living through a golden age of solar discovery. Right now, at this precise moment in history, we are positioned in a scientific sweet spot, a Goldilocks era for understanding coronal mass ejections unlike any before. For the first time, we are not staring at the sun with a single, blurry telescope. We have surrounded our star with an unprecedented fleet of robotic observers, each with a unique vantage point and purpose. The Solar Dynamics Observatory watches the sun unblinkingly in high definition, capturing every magnetic twist and flare in stunning detail. The Parker Solar Probe does what was once thought impossible. It flies directly through the sun's outer atmosphere, tasting the solar wind and feeling the structure of coronal mass ejections at their source. And the Solar Orbiter journeys to view the sun's poles, the mysterious regions where the global magnetic field is generated and recycled. These are not isolated instruments, they are a coordinated network, a symphony of observation providing a continuous, three-dimensional data stream of our star's behavior. And this technological revolution is happening at the exact right time. Solar activity is not quiet, it is ramping up towards the predicted peak of solar cycle 25. The sun is becoming more active, more volatile, meaning more frequent and potentially more powerful coronal mass ejections are being launched into the solar system. This is the critical combination: an active, erupting star and a swarm of advanced probes ready to catch every detail. Scientists are no longer forced to piece together a storm's story from a single, distant snapshot. Now they can watch an eruption from its birth in the photosphere, track it as it accelerates through the corona, measure its internal magnetic chaos as it passes one spacecraft, and then observe its impact on another planet or a satellite closer to home. This multi-perspective view is allowing them to test long-held theories about how these storms form, accelerate, and evolve during their journey. It is turning space weather forecasting from an art of educated guesswork into a rigorous science of modeling and prediction. We are, in essence, watching the sun's fury with more eyes and better tools than ever imagined, during a period when it is most eager to show us its power. This moment will not last forever. The solar cycle will eventually wane and our fleet of probes will age. But for now, we are seated in the front row of the greatest cosmic laboratory imaginable, witnessing the violent mechanics of our star in real time, gathering the knowledge that may one day allow us to predict, and perhaps even protect ourselves from, the next billion-ton storm it hurls our way. This journey through 20 bizarre facts reveals a profound truth: coronal mass ejections are the solar system's great connectors. They are not isolated explosions, but the primary threads weaving together the sun, the planets, and the delicate fabric of life and technology that clings to them. From ghostly stealth storms that slip past our watch to cannibal eruptions that build in transit, from the fossil records on the moon to the biological compasses scrambled in migrating birds, these events demonstrate a reach far beyond the beautiful auroras they paint. They are a fundamental force, one that may have forged life's building blocks in Earth's primordial sky, and now holds the power to unravel the technological tapestry of our modern world. Understanding them is no longer a niche scientific pursuit. It is an essential act of planetary stewardship. Our safety depends on vigilance. You can be part of that watch. Follow the forecasts from the National Oceanic and Atmospheric Administration's Space Weather Prediction Center and take a moment to simply look up. The sun is always turning, and the next chapter in this ancient, violent, and beautiful story could be written across our sky at any moment.